Hello, my name is Thizirie and welcome to Summer of High Performance Computing. My project is about high-performance machine learning. It is about studying how can HPC tools improve machine learning algorithms, especially compared to GVM-based technologies. Let's dive into these notions. You may have heard about neural networks, machine learning, big data, and so on. We will start by giving some definitions here, then talk about how useful the different algorithms can be and in which cases they are more suitable. After that, we will take a more detailed look at the machine learning algorithm we worked on this summer, and explain why we are doing this and using HPC to improve its efficiency. Neural networks is a series of algorithms that aims to find underlying relationships in a dataset through a process that is similar to the way our brains work. It is different from machine learning, which is also a set of algorithms, but it parses the data and finds patterns between the parsed data. Machine learning algorithms can only learn from previous decisions. Our project will focus on machine learning. Our algorithm is called gradient boosting. And you know what? It's actually one of the most popular algorithms used by the biggest Kygo competitions winners. They use a famous library called XGBoost. In fact, it is all about creating trees considering the data we have and the errors made by the previous iteration's trees. But wait, what's a decision tree? A decision tree is a flowchart-like structure, where every internal node represents a question or a condition. The branches represent the outcome to the question. The end of the branch that doesn't split anymore is a decision or the leaf. As an example, I will use my super small but cool dataset I created only for you. You can see here that, for example, if I want to predict how cool is a person, I could choose as a condition loves HPC greater than or equal to 5. I would end up predicting, for instance, that the fourth person and the third one have similar cool grades. Then I would choose another condition to split again one group to have more accurate results. Now we can talk about what we did. We implemented an independent decision tree. This means that it is able to choose the best condition for each internal node by itself, by calculating how impure is each child node created by one condition and choosing the best options, and repeats until it can't split anymore a node. We have several stopping criteria. Then this code is included in another one which makes it gradient boosted. Now, of course you may ask, what is gradient boosting? It is a machine learning algorithm that produces a predictive model in the form of an ensemble of weak prediction models. Here, these are the decision trees. We iterate 100 times this algorithm. This creates 100 decision trees that have different criteria and considers at each iteration the errors that the previous tree has made. It doesn't give more weight to any of the trees, but the tree number I will focus on the individuals that didn't fit into their leaves in the tree number I-1. All this work can be very slow if you have lots of data and possible criteria. And to get some good predictions, you actually need lots of data. And here is where HPC comes to save us. The parallelization part with MPI and GASP could touch different aspects of the algorithm, but as you may have noticed, we can't parallelize the algorithm of gradient-boosted trees itself since each iteration needs the results of the previous one. These are not independent, so we will directly work on the decision tree algorithm and parallelize it by sharing the work of the function that finds the best condition to split a node between the different processors. I hope that this video helped you understand machine learning and how can HPC help to improve our algorithms' efficiency. If you want to know more, check out my blog post and final report. Last but not least, I would like to thank my mentors Michal Pitonak and Marian Gal for their help and support and praise for this opportunity.